so that it's not confused with our thanks for the talk, let's thank Felix for the workshop. You know why they call it a workshop? Because he did so much work to get it to that. Okay. So the talk now is not titled TBA. It's titled Geometry in Modal HoTT.
Thank you, Steve. Yeah. I must say I had a lot of help. For example, Steve advised me on a lot of steps. I always went to him, and should I do it like this? And it's one of his one-line emails, good, as reply. Yeah. So, and I had help of all the locals.
Yeah, let's thank Mary Grace too. She was a big help.
Yeah. And of course, I'm very happy how things went, and most of the mass of nice things that make me happy the last weeks is coming from the participants. So thank you very much for being here and yeah, doing so much stuff around me. So it's hard to keep track. So my talk is a bit spontaneous. I didn't realize there's an open spot until yesterday. And what I'm going to do is mostly tell you things I've already told somewhere. And yeah, it's going to be the things I most liked from my work. So yeah, that's the criteria for selection. So nothing really new. So what I want to explain a bit more or zoom in on is this situation with this modality im or I or the Rahmen shape or co-reduction. So that's something I will assume throughout. So let I be a modality. So I'm not really assuming anything else about it besides being a monadic modality. And yeah, what you can think of is co-reduction. And what this means, quick reminder, for example, for sheaves on finitely presented K-algebras or some field, you could define it pointwise like this. I mostly mention it because I will do a variant later. And this reducing in the argument is, well, visually something like identifying infinitesimals. So I want to draw a picture. Both, I guess, was already very close to making the same remark. So say we have some surface, smooth manifold, called X, and we map it to its image under I. What will it look like? Well, it will look like exactly the same. So, at least unless you don't magnify a lot. So you have to magnify. Let's say we pick a point and magnify around it. Then what we see is around some actual point X, there are a lot of infinitesimals distributed around. And what it does by this algebraic stuff, if you don't know what it does, don't care too much about it, is it identifies all those infinitesimals with this one point X. So what we map this magnification to is, again, the point. And for all infinitesimals, we throw in an equality. So this formal neighborhood, this infinitesimals around the point get contracted to just a point. Okay, so it's gone. And what David emphasized nicely in the beginning of the week is that doing geometry in this topos via this modality works by describing how we remove what we are interested in. And this means we can look at the fibers of this quotient process to get to the interesting information, this infinitesimals at some point. So this is a more formal word now. I make some formal definition to be read as type theory. So if we have some type A and some point x, then we can define the formal disk. They appeared a lot in those talks and in Eckbert's talk, just as fibers with other special name. And what we do is we define the collection of all these infinitesimals around some point by just saying, well, collect all infinitesimally close point around x. And how we can say this is by using the map here, just denoted eta, the unit of our modality. And if we map over there, we get some relation we could call infinitesimally close. If you read eta a empty equals eta a other argument empty, then you could read this as a relation is infinitesimally close in A. And in my Hector code, I actually write it like this. So this would then read as sum of our infinitesimals to x. Okay, then this thing is the what's called the formal disk at x. Okay, and what works pretty well is to view this as some kind of infinitesimal version of analysis or differential geometry. So one basic notion is to define a derivative. So for, and to remind you, every type we have is supposed to be smooth in some sense, or has some differential geometric structure. So we can always define a derivative, and this derivative goes from between the formal disks. So df and some point in the domain, let dfx from dx to df of x. So it's really a dependent function. The map given by, well, we have a sigma type here, so it will contain some pairs of y and some witness that something is infinitesimally close, so I call it epsilon. So we map a pair like this, well, to the image of the point, which is supposed to be infinitesimally close at x, at f of x, to f of x, because maps happen to all preserve the structure. And here, well, we can almost say just use the map on the infinitesimally closeness witness, but we actually have to commute here a bit. We just add this thing, then we have to use naturality of eta. So I just say plus naturality eta. Do it the right way. And yeah, then it's done. Then you have this derivative. Derivative is a bit misleading. Maybe you could also say completion if you're close to geometry. And yeah, what it does is, in this case, it actually contains the differentials of all orders. So it's a bit more than the usual derivative. And this is a particularly easy case. So if you only want first order infinitesimals, you have to do it a bit different and also a bit less nice. So let me briefly sketch an idea I have how to do this. So don't take it too seriously. I have computed almost nothing about it. I just assume it works. So idea for specific orders is you define a sequence of modalities by saying IN is given pointwise again by modding out the nil radical to n plus 1. You can take the power of an ideal. And what it means, for example, for the case, so let's just look at it in this case. So what follows from this I0 will be the old I from above. And what it does in this case, I visualize as follows. So again, if I have my point with a lot of infinitesimals around it,
Yeah, they're hard to see.
Like this. Yeah, I magnify a bit more. So we have some specific infinitesimals lying around here. And what this does is it only collects those which are far away. So higher order infinitesimals. Lower order means they are very close. Like a square zero infinitesimal is closer than a x to the 3 infinitesimal because you only have to square it to make it 0. So, to move it less. Okay, so what happens with this situation? There's some infinitesimals and you only kind of move them in beyond some boundary. So maybe this one stays. So you don't reduce to just a point, but to some tiny surrounding you can call dx1. Which means you could define a first order, let's call this eta 0 x and eta 1 x. Then you have an eta 1 0 x or something like this up here, induced by the universal properties of modalities. And you could look at the fiber of this one instead of the fiber of just eta. So above here, that's actually also a fiber or cubic. And here we would have to work with this. But I think if you write it down in type theory, it's not really harder than this one. So some things stop to work. So maybe you want to keep this in mind. But yeah, there are very different approaches to fix the problem that you only have all orders here at once. So you could also start to do synthetic differential geometry. Just throw it into HoTT. Why not? But then you have to calculate with numbers again. And I really like this very abstract approach. So I'm more for this approach where you have a sequence of modalities. So I think that's cleaner in some way. And okay. Questions so far? Good. Maybe. Okay. No.
I wanted to say it also naturally connects actually to the actual shape. All of these are kind of infinitesimal shape operations. The actual shape is the thing that contracts something even bigger, namely the non-formal and non-German in actual open neighborhood.
Yeah.
And there would even be one in between, the one that contracts germs, and then the sequence of guys.
Yeah.
And they would. May I just make another remark? I'm just doing it right now. So, so one thing I kept speculating about in emails to Felix, which he wisely ignored is that there's also this option of using that supermodality at the end of this tower. So at least in the models, right, the super infinitesimals have a special property that they're all first order by this I amplified. So as you go all the way there, there's some first order information, at least in the model.
Yeah, you can at least get some first order disks. So
yes.
So yeah. I tried to understand, and I think I managed, but then I wanted this. But yeah, anyway, I don't know how this is. Okay, so here are some more hints how this stuff looks externally. For how much time did I use already? Okay. Anyway, external examples, or let's say remarks. So, for example, if I say X is the affine line, like this, then D at 0 will be given as a formal scheme of the power series, topologized in the usual way. And also something which came up as a question, I think it was just briefly answered. Let me briefly answer it again. If I have a morphism of schemes, then in precisely this setup, I know that if F is formally at heart, in the sense of EGA, then F is, if and only if F is etal for this modality I in the sense of Egbert's talk. So I guess it's a clarifying point. And something to be aware of, if I again take this X and I apply I to it, the result will be a sheaf. So this works for anything between the risky and etal topology, or pre-sheaves, if you like. And if I apply it to a scheme like this, for example, the affine line, the result will not be affine. So people always ask this, and no, it almost always destroys being affine, so you can't see it really in regular scheme theory like this. So don't try. You need sheaves for this. Okay. Yeah, some small remark, which is trivial, but maybe a bit enlightening to this situation. So if I take Ix for any space, then all these formal neighborhoods are trivial. That's basically the picture up here. It's immediately clear internally because your eta will be an equivalence. And we talked about its fibers.
For what case? For X?
For X, any type. Strange. Should I write it? No?
Oh, if it's already.
Yeah. If I apply I to it, the result will look as described here in this picture. So that's D, let's say eta X. It's just a point here.
If X, you take I of X. That's what you're saying. I is I.
Yes. Yeah. So I just wanted to formally say that's how it matches to this one, to this equation. Okay. So it's easy to make some statements about this. So this is also again trivial. If you remember Wellens talk, which just said I et al. Just means the naturality square for F is a pullback. So if you apply I, you preserve equivalences, so you have a pullback square. And if F is I et al., that's also something Egbert proved yesterday in his talk. You induce, so he wrote it with fibers, but those fibers are now formal disks. And the statement was that an et al. Map induces equivalences on those fibers. And those fibers are exactly the maps we defined earlier. Something abstract from Egbert's talk tell us these are all equivalences.
But in the first place, it should. You mean really an only if there?
Yeah.
Not yet. So that's also something we talked about in Egbert's talk. So if I throw in that, and I checked which one I have to throw in, if this map is surjective, the eta, then I can go back. So it's a bit like saying, in this case, I mean a local diffeomorphism, induced isomorphism in tangent spaces. And here you, in this generality, you can only go back if this map is surjective, but that would be externally a consequence of X being formally smooth, but not an if and only if. So
I think the question is about A, part A.
You just mean
You don't really mean if and only if in part A.
oh, yeah, that's very wrong. Sorry. Next. Yeah, sure. Okay. Then some, well, you could see it as a reformulation of this, but you can also directly prove it. And I guess I take the time. Because for this kind of maps, I think it's really a nice theory. So again, if you still have this condition, then you have F is I et al., so same thing here, if and only if. So it's again for all X and X suppressed here. Now I say it because I want to define Y to be f of X. We have that the following pullback square. So how it makes sense, I will tell you in a moment. That's fine. So this is you pick a point here, go down, build the formal disk around the point, and then you take a pullback. And if this pullback turns out to be this product for all choices of point here, you can conclude that F is formally et al. And in the other direction, yeah, you get this square as a consequence. And I think it's a nice picture because what it basically tells you is that over all formal disks, so like this, it's here, it's included in the big not so formal space, space up here. And if you look at the pre-image, and F is formally et al., you get a decomposition into copies of the formal disk down here. So, and the decomposition is disjoint in some infinitesimal sense because we make a product here with something modal for this modality, which means all formal disks are trivial. So here you can't move infinitesimally between these copies, but they might be still really close to each other.
Do you have an example for a non-surjective eta in some model?
No. I mean, yes, you can take pre-sheaves, but that's a bit boring. You just take pre-sheaves up here and take a not formally smooth scheme like kx, y, ax times y, or something like that, coordinate cross. And then you see that you take the condition from EGA, which is basically a lifting property, and this lifting property will tell you precisely that eta is not surjective, pointwise, not pointwise surjective.
Also, a topological localization won't have eta surjective in general. So if I take the open or closed subtopos of a proposition.
Yeah, right. If you take general modalities, there are lots of sense. Yeah.
So your picture sort of looks like a covering space condition. Is there a relation?
Yeah.
That's why it's called
That's why I
formally
like it.
HoTT, right? It means
Yeah.
infinitesimal. It looks like a covering space. That's what I mean. Right? HoTT space is covering space.
Oh, I meant is there a literal, because this is for a general modality.
I'll come to it later, I guess. Okay, so now Urs in his talk also mentioned that I use homogeneous spaces as basic model spaces for the V manifolds. And yeah, I'd just like to expand a bit on those and how you can construct these trivial G structures, because, mostly because it's really easy and you don't really have to do anything. So you can just do it. And I mean, when I say you can just do it, it took me some years to get used to this situation, especially this modality, HoTT, with its quality types and dependency and its universe and all this stuff. But once you're in it, so I guess you're just missing this modality, if at all. So intuition for this. But if you have this, lots of things are really easy. So I would even say easier than in normal calculus. But yeah, just follow full of things. Okay, so these homogeneous spaces are defined like follows. Type V is homogeneous if there are, if you have a point, something like a neutral element, a family of translations that can translate your given point to any other point. So that's not yet in the type here. And I usually just say they are equivalences. And what we also want to have is a witness that what I just said really is correct. And if you translate E, you get X. So that's all. And how I came up with is I just looked what do I need in my proofs. So there's nothing more to it, but it works really well. Okay, and what I can do now is now I can already prove the theorem which was used. And what it says is, in a more type-theoretic way to express it, if V is a homogeneous space, then all its formal disks are equal. So literally, not merely. We can really formulate it as a pi. Dx equals d. So for the smart people, maybe some passing help. Or another way to state it, which might be a bit more normal in some sense, is if I take the bundle of all formal disks, so the formal disk bundle, I can compare it to the trivial bundle. So I just take the formal disk at some point, and this will actually be the same. It's the same statement to say that we have an equivalence over the projections. Okay, so that's the analog here of the classical theorem, for example, that the tangent bundle of a Lie group is trivialized by translations. And here's how you prove it. You just take your translations and derive them. So you take D of this map and then look at its differential at E. And just from typing, this is a map from dE to dTx of E. And by knowing that equivalences are formally étale, and formally étale maps induce isos as differentials by equivalences, use an equivalence. And then by this condition, you can just apply this to the form disks. So we know we have a equality between those two things. And yeah, this is also an equality, so we can just compose. So what we get is some term phi x in, yeah, let's do this way, dE equals dx. So that's this thing, and that's also easy to use to construct this map. So I won't mention it here. And by now, I like this way of phrasing it more. And I mean, you could also compare it to traditional geometry in a different way. You could say this is something like a differential form with value maybe in some Lie algebra, I don't know. So with transformations of your form disk here, you have something which varies in V and gives you such transformations, and that encodes how your bundle is trivialized. Okay, so yeah, one important point here. So far, type theoretically, it's all trivial proofs, but I came up with it in a non-trivial way. So Urs also highlighted this a bit. So I started with his ideas and ways of proving things, which are really nice, I must say. So I had a lot of fun pasting Pullback squares and doing lots of stuff, which also gives you a proof of this one, some of the desired generality. But later on in some other theorem, so I did this in Acta, I figured out that what I really need is a term of this type. And then I just went back and said, yeah, how can I produce it from my theory? I thought, well, I could build it from this, but it's a bit annoying. So let's see, can I just produce it more directly? Now I just went back to all of my thesis so far and yeah, basically threw away a lot of stuff and replaced it by the arguments I just gave you. And that's for me the decisive argument for using this framework. So that's a point that worked for me better than expected. Yeah. Okay.
Felix, maybe just simplify this point about the differential forms. You want to say that's the Modal HoTT form, which
yeah,
is a famous thing. Yeah. When a group, just simplify, when a group V and the Modal HoTT form is defined to be that left invariant, so translation variant differential form, which on the neutral element as a map from the tangent space to the Lie algebra is the identity. And that's the identity. Right? The Lie algebra is not dE. The tangent space is also dx.
Yeah, not literally, yes, but
the jet.
Yes.
Jet Modal HoTT form.
To some transformation. Yeah. Okay. And yeah, maybe. Yeah, maybe I'll say later some more about this. For the connection. Yeah, since it came up, I want to briefly mention how you see the trivial G structure from this thing because it's just so easy. So remark for V homogeneous again is a trivial, so it's just a name here, G structure which means you have some triangle like this. With some pointwise equality or truth in here. And maybe let's just do it below. What can I do? I can first factor the problem a bit. So if we have some G as a subgroup of odd DE, we have a pointed map, so we have a triangle like this. This is just a point. It's just a pointedness here. And this map down here, the classifying map of the formal disk bundle is just the map that sends a point, the dependent map that sends a point to the formal disk at the point. So I have some X in V. This map down here is given by, well, E or TE is some sigma of types in the universe that are merely equivalent to DE. So I have a sigma, and the first component is the formal disk at X. And the second one we just produced, even something better. We have this phi X from the proof or from the statement, an equality between dx and dE. So we have to just truncate it. So maybe that's so we can just propositionally truncate psi at X. And we've produced this map. And when we want to construct this triangle, we have to prove, so here we just include the point. So we have to prove that all our values, our images of points, are equal to the point over here. And the point is dE. So we have to prove dx is equal to dE, which we already did. So this homotopy, or equality of maps, is given by psi. I could have written it in here. That's just psi, and we are done. So in some sense, this trivial G structure is this Mauer-Cartan form, if we want to call it that. Okay. Yeah, there's something I wanted to mention which maybe remembers you of something from the differential geometry textbook. It didn't remember me, Urs told me, so at some point I came to him with some equations and you could see the light between the lines and tell me left invariance, Mauer-Cartan forms. So remark, if V is an actual group, or a zero group, then maybe let's call this thing theta, then theta is left invariant. Which means theta at E is the identity on the E, and for any translation, if we translate theta by the translation, so the whole thing, then it is still theta. So in type theory speak, this could be translated as Tx star, which I tell you in a minute what it is exactly, is theta again. So, yeah, let me talk about this star.
Tell us first what a zero group is.
Just
A
a
zero
group.
type.
Yeah, zero type, that is.
You also notice that one group sometimes.
Yeah.
Oh, really? Okay, I'm confused. Yeah.
Step before two group.
Okay. Fun thing. Okay. Maybe I should call it. Yeah, I should call it.
Wait, what was the reason for the one group? Because the categorical case is known as a two group.
Yeah.
So we're back. Usual groups have to be called one groups. We stick to that.
Yeah, it seems good to start calling it zero, but it seems funny to call ordinary concept zero concept.
Okay. If we have some formally a map from something else to B, we can pull back our G structure. So, but I do it in 2 steps. So the first thing we get from this formally a map is a triangle, so like this. F. And formally a means the differential will be an equality between the formal disk here at a point and the formal disk at its image. So we know we have an equality here, which is literally just the differential. So yeah, it's a 2-cell. And if we have this 2-cell, well, I've drawn it not in a good order, then we can just paste this 2-cell at this cells over there, and then we get a pullback. And should be a G structure and star theta, so we can pull back this one on B prime, given by pasting. Okay, and by the way, this remark David had with the chain rule being dependent composition, and that being something which is nice for us, but not so helpful for your undergrads that learn calculus. Here's another thing that's nice for us, at least for me, and not helpful to undergrads. If you do this with 2 maps, you can, well, paste this and then paste that, or you can paste the composition, because that will also be formally et al. And the chain rule, of course, tells you there's a 3-cell between this composition 2-cell, this 2-cell, so you can see the chain rule also has a 3-cell in here. So, and yeah, maybe one day, I'm dreaming of having maybe directed univalence, then you can do it for all maps. So you don't have to restrict this pasting stuff from the ones. Yeah, but anyway, okay. So that's how you put back, and that's how you get some equation which looks classically. Steve, can you tell me how much time I have left?
15 minutes.
15. Okay. Yeah. It's on board. Maybe this one.
By the way, what I clearing the board just for amplification, what you just said as a remark is a famous fact from standard differential geometry, which says that metric structure on a space does not pull back, like Riemann metric conformal structure, symplectic structure, does not in general pull back along general and smooth maps, but it does pull back along local diffeomorphisms. In the standard context, you see this, for instance, in the Riemann metric. It's a which is a special case of this, a classically a rank 2 tensor with a non-degeneracy condition. When you put it back, you still have a rank 2 tensor, but if it's not a local diff, it's no longer non-degenerate. So that's a famous sort of fact actually about Cartan geometry. Found useful there.
Yeah, I mean, I can translate it if my web is not locally diffeomorphism. It's not necessarily an invertible two-cell. And if I paste it onto that, it will lose its invertibility. Yeah. That's something I can understand. Okay, so that's something a couple of people ask, and I also find nice and want to tell you is what happens if you switch modalities. So this is all for some arbitrary modality. So what happens if you exchange it for other stuff? So I can just make this more clean and tell you what we know so far. So et al. For modality, in this case, some asterisk, and maybe that's how you should read the whole table. This is formally et al. And this dx is a forming disk. And some other fun modality that I failed to see as some problems. Yeah, Ulrich mentioned it. So when I first thought about, can I compose truncation with shape? I thought, yeah, obviously, because truncation preserves discrete types, but actually in Mike's setup, it's only known crisply. So if I do it this way, it's not really clear if it's a modality, but Ulrich already mentioned a fix. I could just throw in both generators, just nullify the appropriate sphere and the real line. So that's how I could define it, and then it hopefully does what I want. Okay, so in this case, there's some piling up evidence that this is, or this class contains covering spaces. And the form disk in this case, and that works always, is the universal cover. Which also means if you just take shape, you get some interesting, at least I find them very interesting, generalizations of this stuff. So you can also n-truncate, of course, to get something in between, but let's just mention it like this, some interesting generalization of this. And yeah, here as well. And what's also not so much spectacular at first glance, I guess, but I guess it's pretty important, is if you take sharp, you get what in Germany is called Spur topology, and I think the right translation is final topology. So final map with final topology on domain. And here I don't know. Maybe David knows. So I'm a bit puzzled by that. Is it containing a form of this?
It contains the form of this.
It contains
And
the form of this.
particularly nice spaces with your definition of pi, for example, the affine line, it will equal the form of this.
Cool. Thanks. Yes.
So the shape, you say something interesting, but it's, I mean, it's a locally constant sheaf of homogeneous types. Locally constant sheaves. Felix,
I guess that for the sharp, in the case that the map is in addition, the sharp
Yeah.
model map is in addition mono, then this is good because these are the embeddings.
yeah, subspaces. So
Yes, the subspace included.
yeah,
So this will be important. Now you can say within, you can say inversion. One, right? Sharp, you can say embedding. Together, that gives you a basis of manifolds, which is important for knot theory stuff.
yeah, right. That's why I said I think it's important because lets us speak about subspaces. So, yeah. Right. Thanks. Okay, so yeah. Yeah. So when I thought about this one, I came to look up on Wikipedia what it's called in English, right? Because yeah, I only knew the German word because it's so long ago that I learned about it. And the Wikipedia page said, well, here's how final topology is defined in an abstract definition. And then it says, but in the formal sense of category theory, this is not a universal property. So here this one, here's a pullback. But I guess if you make a statement that something is not given by a universal property, kind of deserve to be wrong. So if you have a square like this, then I mean you can take a textbook and it will say, tell you X carries the final topology with respect to this map and the topology down here. For every other map like this, that has a lift on the level of sets. And this condition is just that you have a map to sharp X. If for every situation like this, you have a induced continuous map here. So usually it's that then this map is already continuous. So that's how it phrased, and here becomes a product. So maybe some advance on justifying this one. If you say let X be a connected topological space. So if you're in recohesion, pointed is also something I would like. If you're in recohesion, you could say this is 1 and point. And it's a 0 type, maybe. Yeah. And then you could say, if I have now the X is below because it's about covering spaces. If you have some map into X such that this square is a pullback, which means the map is then, well, then there's a lifting criterion for topological spaces where you say something similar to up here. So you say for every map of topological spaces, usually you have some connectedness assumptions, and in cohesion you have this local contractibility, which just kills a lot of this stuff, so it becomes easier. So it's a bit of cheating here. And yeah, for every map like this, such that, so that's a map phi, such that if you apply the fundamental group functor, then the image of the fundamental group of Z, which shall be pointed, lies in the fundamental group of Y, which is a subset of this fundamental group because it's a covering space. So that's how it's written in Hatcher. But here, to make some sense of it, first, well, to connect these two things, I mean, what this shape is, if you want to truncate it, is a de-looping of its fundamental group. So up here, you can prove abstractly from this being a pullback, that's pretty easy, that this will be an inclusion of a subgroup. So that's something you already have. So in this case, that means this is 0 truncated. Yes.
Why?
Do I have? Why? Good question.
It's an extra, if it is 0 truncated, then it's an actual covering space. But in general, it might not be. It might just be some group homomorphism.
Oh, sorry. Yeah. I'm forgetting again. I said, I almost said it, but let's just say everything on this side is a 0 type. So thank you. So in this case, we know if you look at a fiber of this one, it's 0 truncated because of pullback pasting. So we know this is 0 truncated. So we know the maps between the groups is -1 truncated, i.e. it's a subgroup. So it's directly from the pullback condition. And now if we pass this condition while applying the pi1 functor to a map, means we apply our shape functor. So we have a shape of Z here, more or less its fundamental group, and we have some map over here, the image of phi. And this means it lies in the image of this map on the level of actual groups. And we have an equivalence of categories, Ulrich probably mentioned in his talk, in the first one. So this means we can lift this map. So we have one up here. And now we have a cone for the pullback. We have one, and now we can lift this map here. And that's what this Lemon hedges is. Okay, that's my justification for saying covering space. And 5. Okay. Then I kill this.
The y is 2. Yeah, so everything in the left, so x and y. So usually 0 times. Yeah, force the covering space.
Oh, x and y. Yeah. So that's connected for x. Don't really want it for y. So y also is a type. Yeah. Right. That's what I want.
Since we're working in a cohesive setting, these are not just sets.
So if you include some nice topological spaces in one of the models for real cohesion, do it by homing in and you land in the 0 types. So that's why I associate topological space with 0 type. Okay, now remember from Egbert's last talk, there was a theory, the modal descent. What it tells you is if you look at maps, so I repeat it with the circle, if you look at maps like this, so for any fixed x, then this is the same as étale maps into x. So this time it's called y, u, y to x, circular étale. So basically tells you that on formally étale maps, you don't, or on circular étale maps, you don't lose information when you apply your modality. And now let's just say this situation again, x pointed, connected, 0 type. So connected, sorry, I guess it's better if I just write it out. So truncation of its shape is trivial, connected as a topological space, not as a homotopy type. So X like this. Yeah, oh, that's all I need. Ulrich will tell you. Okay, then I just repeat what's here. So we have the universe of one-shaped things. I didn't introduce this to you. So like this. And here we have the one shape of X. And this thing is the same. So I'm just repeating it, but I will kind of move things, explain things around in a minute. So it's the same as shape 1 ether maps, which I argued are covering spaces into X, or covering spaces over X. So what I can do is I can restrict this equivalence to things that have zero truncated fibers. It's more like actual covering spaces. And this commutes. So I can just push it over. But let me reformulate it a bit more. So I said, this is B of the fundamental group. So I could say this is maps B pi 1x into the universe. And now I'm truncating the fibers. So it's zero truncated shapes or discrete zero types. That's here. And I can, commuting with everything, go down here. So what I get is all ether maps. So shape 1 ether, zero truncated fibers. Which are, with this argument, a lot like covering spaces. And up here, that's just actions of the fundamental group on some discrete type, so a set. So I have actions on sets are the same as covering spaces over some space. So you can use this abstract thing to recover what is known as fundamental theorem or covering theory. And what's nice, you can just also drop the truncation or do some other truncation, so you get a lot more theorems, generalized style stuff. Okay, thank you.
There must be some questions.
I'm asking a question from that.
Okay.
What would happen if you defined the formal disk with a propositional truncation? Would much of the theory still go through? Like it's right behind you. So if you just stuck that they were nearly equal in the modality,
Like this.
yeah, because this has the interesting consequence that now the formal disk is a subtype of A in some sense.
Oh, that's interesting.
And it has the second consequence that there's a natural filtration that might be the disks.
I mean,
Because you have, because of Egbert's theorem that the -1 truncation is this sequence of joins, you can define the nth order formal disk as n-fold join with this identity type of itself, and it will converge to the infinite disk.
will it be the answer? Will it be the answer or formal disk? Or
I don't know, but
This will already be the infinite order formal disk.
that's what I'm saying. Yeah.
With the intermediate joints.
That was my that was a suggestion on that too. I just
so
wondered. So the first step is just, does this like sort of violate
So how do you draw a
Oh, yes, so
like this?
that's the sort of homotopy theoretic suggestion. And I don't know, it's just
I can understand
Yeah,
it.
that's a candidate for the and for model.
because it has this nice fact that the colimit on as n goes to infinity is now d infinity, if we define dx to be d infinity. And these relations are no longer transitive, sort of exactly like you would expect the nth order relation not to be transitive. But if you're nth order close and nth order close, then you're n plus nth order close, the two things, right? So it has this kind of additivity property. So anyway, it's just a suggestion. It's
Yeah.
just kind of a
Yeah. Just
X
don't know.
starts out being a zero type, then don't we know that X is also a zero type? Isn't that
Yes, that's true.
automatically?
Yeah.
But that means that's automatically.
Yeah, for zero types.
yeah,
this
that's why I
doesn't make a
asked. That's
difference.
why I
That's-
asked if
that's
this is
part
a
of this
natural
point.
definition,
Yeah.
because if all the examples that we have are sets, then in all the like with K algebras and whatnot, then they all coincide.
Mhm.
and stuff.
Yeah, no, this is a formula that is expected to be true only in the derived algebraic geometry. Where the mapping of the point to the formal disk is no longer a mono.
Anyway, it's just a variation. I don't know.
But would it supposed to go to topos for derived algebraic geometry? You see, the n truncation will give the nth order derived from this.
No, it's not the n
It's
truncation.
not the n truncation.
It's the n-fold join of the point mapping to the x.
Ah, okay, so can you see if that would
Yeah, there's a formula close to this one that produces the completion.
that would be
So we can discuss it.
I don't know, it's like this. Yeah.
So yeah, so here, if you would take the equation of the diagonal to x infinity, you could start producing the n-fold join of S1.
I don't know. It's just
Yeah, thanks.
do you know offhand if much of the theory that you did? It seems like most of the things you said work with this definition exactly the same way. I don't see anything that you said. That's what I
Also
thought.
don't see a problem.
Okay.
I have a more speculative question. So some of these examples that you've done, like this proof of the fundamental theorem of cover spaces, there's an apparent violation of the law of conservation of difficulty. And I invite you to speculate on whether that really is a violation, or if the explanation is just that in order to really get the same theorem back out, you'd have to put an equal amount of work into verifying that you have a model.
Yeah, you have certainly to put a lot of work into that. And I mean, the shape functor exists and is as nice as it is. It's by no means clear. And I mean, in real cohesion, as I most recently experienced, you can also easily make mistakes. It's still some good setup. You can overlook problems.
So
Yeah, but it's really a lot easier when you say do it with an abstract modality.
So what we get
And
is
and
at a high
it's
level.
of course about less spaces. I mean,
This is about
less topological spaces, but then you throw in all these topological stacks. It's again something nice, I guess, because when I looked around and entered covering theory for topological stacks, only found very complicated stuff and some weird incomplete end-up entries.
further questions? Rich, do you want to give us a last comment here? This is the end of the meeting.
Oh, wow.
Give us a reflection. Give us a reflection on where we should go from here in modal homotopy type theory.
And please mention Nickel.
Oh, that catches me unprepared now.
Yeah. That's okay.
Yeah, so, well, I think what I found fascinating in this meeting is that somehow just things start to work now. It keeps to work. So we have, I think, an amazing connection between people just doing computation, actually, and computer science. And I had given this weird talk on string theory, and somehow it's actually all coming together. So I think that's fascinating. That wasn't the case just a few years back. Right, so maybe one thing that should be done now is, so Felix gave this table up there with the different modalities that are all modalities. And so, of course, there's some little gap there, because what this table is really doing is not taking one and the same modality in the type theory and interpreting it in different models, right? And only this way you get a table, otherwise it will just all collapse to one thing. So what is necessary there is to find an internal way to distinguish these modalities, and that's where the suggestion comes in that you should see that they're organized in some progression of the joints, so that actually the internal type theory can see them as distinct. That should be done. My understanding is that's sort of a bit away, but I think that's really important to make this table really be there in the type theory. And then another thing I found interesting during this workshop, which connects to what Eric just said, that there might be a good chance actually that many of these, maybe much of the sequence of the modalities, the progression, might actually be constructible just internally without assuming anything about the side. So with David's talk, we got this idea that actually what we might just start out as follows. We might just say, okay, we're in type theory. Now let's start with how much can we get. So we start by saying maybe let's declare sharp to be given by not, right? More or less. So yeah, that's not theorem. And then once we have that, we can say, okay, let's look at the types that are nullified, quantified by that. These would be the formal disks, and we can organize the formal disks to get im. But we can also, as I think Felix kept emphasizing, then use the formal disk to extract the smooth real line. So one defect of Mike's real cohesion is that its real line is the topological real line. It's not a defect, but it means that there's no none of this. Felix said on the board, nothing of this exists in Mike's real cohesion because that's a topological real line. It doesn't have any infinitesimals. You know? So one open question is how to get the smooth real line. And Felix was making this point, well, which maybe goes actually back to Lavier again, that if you do have the,
I just know it from David.
yeah, but I think Lavier mentions to me something like that. Anyway, so yeah, maybe it goes back to you. There's this observation that if you, for instance, take the first order, just for the sake of argument, first order disk in 1D, the abstract tangent vector, then the point it comes from that to itself, that is R1. It just says that as you map that D1 to itself, you just have this linear choice of how to rescale that single infinitesimal generator. So that
This is.
yeah, that's the idea. So if we use not to get sharp and sharp to get the infinitesimal disk, and then maybe no, but yeah, then maybe use that trick that Eric mentioned to know what first order is. Then we might be able to actually define R1 intrinsically. And now we have all the ingredients actually in principle that should give the first 6 of the modalities in the tower. More or less, you know, it's a sketch. But that would be really interesting if all this stuff were actually just there and you wouldn't have to axiommatize it at all, you would just have to discover it.
It's maybe notable that in that paper of Lavier's, all he assumes about the infinitesimal disk at the start is just that it's a point of type, and then, which is the same setting as the Goodwillie calculus. And so assuming just those assumptions and then doing synthetic differential geometry might turn into Goodwillie calculus. And where these formulas must be the right ones to take.
That's kind of have them.
Okay, well, thanks for those thoughts. Thanks, Urs, for your inspiration. I just want to conclude, I'll get the last word by saying I've been impressed by the high degree of cohesion. I thought it was really cool the way you mentioned a lot of the
That's what we
I don't know if it's related to
So I'm thinking.
There is a way to.